In this lesson, we are going to do a brief introduction to probability distribution functions, which is labeled as PDF, and it's specifically for a discrete random variable. I have discrete underlined because I want to emphasize that word discrete. It's important that you distinguish the difference between discrete and continuous random variables because we have different statistical techniques that we use to analyze each of those types of distributions. So in this section, we're going to focus on the discrete random variables. And a discrete probability distribution has two characteristics in order to call it a probability distribution function. And the two are listed here. We have the first one, each probability needs to be between 0 and 1 inclusive. And then the second one is the sum of the probabilities needs to add to 1. So when we look at our first example, it says a child psychologist is interested in the number of times a newborn baby's crying wakes its mother after midnight. For a random sample of 50 mothers, the following information was obtained. X is going to represent the number of times per week a newborn baby's crying wakes a mother up after midnight. And so for this example, we're going to use 0, 1, 2, 3, 4, 5. And P of X is the probability that X takes on. Okay, so this 0 here is the variable X when X is equal to 0, which means the baby wakes the mother 0 times a week after midnight. Those mothers are very, very lucky. So, and the probability we found that happened is 2 out of 50. And then you can see this is the notation that we use when the variable is equal to 0. Okay, and then for 1, we have that the probability is 11 out of 50, etc., and you can read down the chart. So we're going to verify the two conditions. The first condition is the probability is between 0 and 1. And if you look, all of these values, if I put them in a decimal value, all lie between 0 and 1. So this checks out. Now we have to add up all of those probabilities and make sure that they all add to 1. If I add that all up, I get 2 and 11 is 13. 13, and then I add in the 23, that'll give me 36, and then I add in 9, that will give me 45, and then I add in 4 and 1, that gives me 50 out of 50, which is 1. So that second condition checks out. Okay, now what I'm going to do, even though the question doesn't ask us to do this, I think it's important to visualize what this means. So we're going to draw a histogram and take a look at what this looks like. I'm going to use 6 classes, so each class is one of these random variable values, 0 through 5. Now the probability, let's see, this is going to be 25 out of 50. This is on the side here, I'm going to write the probability. So this will be 5 out of 50, 10 out of 50, 15 out of 50, 20 out of 50. And then this will be 30 out of 50, 35, 40, 45, and then we have 1, which is 50 out of 50. Okay, so if I plot at 0, I'm going to make my bar for 0, which would be up to 2 out of 50. So that bar is going to be really low, 2 out of 50. Then my next bar is going to go up to 11 out of 50. Then my next bar is going to go up to, for x equals 2, it's going to go up to 23 out of 50. Then for x equals 3, that's going to go back down a little bit to 9 out of 50. And then bar 4 is going to be 4 out of 50. And then 5 is 1 out of 50. So this is what the graph of our probability distribution looks like. I wanted to give you a visual representation on what's going on here. The graph of the distribution is shown in this histogram. So because each width of the bar is 1, so this bar represents 0, this bar represents 1, this bar represents 2. There's only one value for each of those bars. So the width is 1, which means the area of the bar, which is a rectangle, length times width, is going to be equal to the probability of that particular outcome. So if I take and look at the bar, say 1, then the probability is going to be equal to the area of that bar. So it gives us a visual representation. The taller the bar, the higher the probability. But then also, if we want to look at an event where we have combined outcomes, all we have to do is add the totals of those bars, and we can have the sum of those areas, which represents a particular event. So for example, if I wanted to find the event of having a 2 or a 3 in this case, it would be equal to the sum of the area of those bars. So if I had, let's say, event A, where it could be a 2 or a 3, the probability of A would be just the sum of those two areas of those bars. So it would be 23 over 50 plus 9 over 50, which would be 31 out of 50. That would be the probability of event A. So I can use this picture to visualize the probabilities of different events. Okay, let's do one more example. This is just a very brief introduction. Let's see. Example says, suppose Nancy has classes 3 days a week. She attends class 3 days a week 80% of the time, 2 days a week 15% of the time, and 1 day a week 4% of the time, and no days 1% of the time. Suppose 1 week is selected at random. We want to, in part A, list the number of days Nancy attends school. So that's going to be what our data represents. So the number of days Nancy attends school, and this is specifically per week. Okay, so that's what the variable represents. Now, because the variable represents the number of days she attends school a week, the values that this could take on could be 0, 1, 2, or 3, right? Because it says in the question that she has classes 3 days a week. So if she attends every class, that would be 3 times a week, or it could go down to 2, 1, or 0. So in part C, it says, suppose 1 week is randomly chosen. We're going to construct a probability distribution, shows that probability, and then we're going to use it to make a histogram like we did in the previous example. So since x takes on the values 0, 1, 2, and 3, we're going to have our variable x here. We'll have 0, 1, 2, and 3. These are the values that they can take on. And this will be the probability of x. 1% of the time, she attends no days for that week. So if we write 1%, if we write it as a decimal, we would write it as 0.01. If we go back up and look, it says for 1 day, she attends 4% of the time. That would be 0.04. Then if we look at the probability of her attending class twice a week, that's 15%, which is 0.15. And then 3 times a week would be 80%, which is 0.80. So here's our probability distribution table. Okay, now let's use it to make a histogram. So over here we'll have the probability, and it always goes up to 1 or 100%, depending on if you're using percents or decimals. And then we're going to have 4 bars, 1 for 0, 1 for 1, 2, and then 3. The chance of her attending class no times during the week is 0.01. So this has a really small bar. The chance of her attending class only 1 time during the week is 0.04. The chances of her attending class twice a week is 15%. And then the chances of her attending classes all 3 days is 80%. So here's what our probability distribution looks like. if we look at the shape of this and we imagine, just a quick review, if we imagine that we connect all the dots here, this is going to be a skewed left. So now if I wanted to use this probability distribution to find a particular event, I have this all organized to do that. So let's say event A is the event that she attends class 0 or 1 day a week. So if I want to find the probability of event A happening, since the width of each of these bars is 1, the area is going to be equal to the width, which is 1, times the height. And the height of the bar is the probability. So if I wanted to find the probability of event A happening, I would come over here and look at this bar. This bar has a probability of 0.01 if I look at the height, but I take 1 times 0.01, that gives me 0.01. Then if I want to find the probability of her attending 1 day a week, that's this bar, I take the width, which is 1, times the height, which is 0.04. And when I multiply that together to get the area, that gives me 0.04. So the probability of her attending 0 or 1 day a week would be 0.05 or 5%. So this is what a discrete probability looks like. Remember, a discrete random variable is a variable that can be counted, like the number of books.